Hello, community! So great that you are back. Yes, of course. Today we talk about agents. What is the latest with AI agents? And what happens if we increase the firepower? What happens if we fire with all agents? We have the perfect star topology, and we're gonna maximize here the entropy. We wanna see the extreme performance that is possible. What is it? Let's discover this AI system. Hello to my channel, and yes, let's start immediately. Now, on social media, you have dozens of how to build AI agents pop up. And even here, you see an archive here, just yesterday, December 9th, 2025. You have here Old Dominion University and even Deloitte and Touche, wow, from the US. And they gave you tips how to build here a production-grade agentic AI workflow with some very interesting graphs. And if you have a look, then they recommend, for example, they analyze this an end-to-end agentic AI workflow, a web search agent, a topic filtering agent, a web scraping agent, a podcast script generation agent, a reasoning agent, a PR agent, an audio script generation agent, and a TTS agent, and a VO3 agent. And would I recommend this? No, not at all. Anyone say why? Welcome, let's start it. Now, just today, December 10th, we have Google launches here managed MCP servers that let AI agents simply plug into its tool. Beautiful agents are sold here as the solution for everything that you can find. And of course, Google is now starting here with MCP servers for Map, BigQuery, the computer engine, and the Kubernetes engine. But please do not forget also the Google MCP security project. And here you have the complete documentation. In general, Google tells us, hey, we are making Google agent ready by design. And this sounds amazing. So you might ask, hey, if I start today, what is the best way to build a multi-agent system, an MAS? Tell me, what is the latest insight? I can only tell you, I'm so glad that you asked, because here we have it. December 9, 2025, we have Google Research, Google DeepMind, and MIT, Massachusetts Institute of Technology published here a brand new paper towards the science of scaling agent system. And this is what we have been waiting for. This is a beautiful study. You have to have a look after you watch this video. So, the prevailing dogma in agentic AI is multi-agent system outperform everything else on this planet. No, because we have collaborative scaling. Now, unfortunately, this new preprint refutes here that universality. Why? Let's have a look. What is the core discovery that Google and MIT had? The performance of an agentic system is not determined by the number of agents. And you say, but wait, you just showed us the publication here from the very same date here by Deloitte and Touche, no? Yeah, but it is not the latest research by them. So, main insight, parallel task like a market analysis, here multi-agent system dominate. You can get a performance gain of over 80% compared to a single agent. A sequential task like Minecraft planning, multi-agents fail, you have a minus 70% loss in the performance. And you might say, hey, wait a minute, you made a mistake. No, it's a plus 70% gain only. No, it is an absolute loss of minus 70% compared to a single agent. And then you have these tool-heavy environments, MCP to the extreme. And adding agents amplifies here the error rates due to, guess what? Context fragmentation. And you say, yeah, it sounds logical, I expected this. But now we have the absolute figures. Google and MIT did an experiment. This is the only way to do it here if you are here in science. And they said, okay, we look here at OpenAI, the GPT system, a GPT-5 Nano, a GPT-5 Mini, and a GPT-5. Then we have from Gemini, a 2.0 Flash, a 2.5 Flash, and a 2.5 Pro. And then we have Claude Anthropic, Sonnet 3.7, Sonnet 4, and Sonnet 4.5. And you see, I love this by Google, they don't show us here the performance of the Gemini 3 Pro, but they make it here, look, this is comparable to the other OpenAI on Claude system. We don't want to show how good we are, so they just use a Gemini 2.5 Pro. But what they have found out is just amazing. They tested now 5 multi-agent architectures. The topology was simple. We have to have a ground truth, the single agent loop, SAS. Then we have an independent, we have N agents working in parallel, and we have a voting at the end. Then we have a centralized MAS, we have a hub and spoke, system. So we have a single orchestrator and multiple sub-agents. Then we have a decentralized multi-agent system, a peer-to-peer mesh system with a debate and a consensus phase. And finally, we have a hybrid system. No? So we have a hierarchical system, but also peer-to-peer communication. I will show you this in a minute. And then we have 4 benchmarks. And they've chosen this benchmark very carefully for agentic properties. Of course, partially observable Markov decision process and multi-step reasoning. No, we really go for the interesting stuff. So they say, okay, let's look what is it if we have a parallelizable job? What is it? A finance agent. Go to the internet and compare 10 developments here from some finance derivatives. You can do this in parallel. So we do have a quantitative reasoning. Then we say, okay, the next thing is what everybody does, a web navigation. So we do have a high entropy and we have a massive exploration phase. And then we have something that is strictly sequential. At first A, then B, then C. Beautiful. This is all that we know from planning. If you have to do a strategy, if you have to plan something, if you have to have a logical argumentation, you have a sequence. And then we do something here, business tools, software development, wherever you use heavy tools. So all the intelligence is now in the tool topology, and we just utilize this and bring all the results back to our main agent or main LLM or VLM or VLA. This is it. Models, tasks, benchmarks, topology, let's go. What were the insights? We have some new physics developed for AI. No, we just discovered some new physics, some new laws that are suddenly possible. The preprint identifies 3 mechanic forces, under quotation mark of course in AI, that determine whether an agent system succeed or if it will fail. At first we have the tool coordination trade-off. No? This is the strongest inhibitory factor in this multi-agent system. So in tool-heavy equipments, if you have a lot of tools, 8, 16 plus tools, the system prompt is massive. No? So when you introduce multi-agent coordination, you introduce here quite a chatter, no? Messages between the agents, and you have a high density in your communication channels. But the context windows, especially if you go with local LLMs that only have, 128K or 256Ks, becomes here really a scarce resource. The overhead of the coordination competes now with the tokens needed for the tool definitions and the reasoning process in general. So even if you have 1 million or 2 million token context window, I immediately run into some limitation if I do this here in theoretical physics. They discovered a law. Can you imagine this? Google and MIT said, hey, we discovered a law here. The delta in the efficiency and the probability of the efficiency is proportional here to a negative numeric factor times here. EC is the coordination efficiency and T is simply the tool count. So recommendation from MIT and Google, do not scale agents in tool-dense environments. The context fragmentation that you will encounter leads to hallucinated tool usage. Absolutely fascinated. I thought we would have solved this. No, simply not. The second is architecture-dependent error amplification. So this simply quantifies how the errors propagate through your network, through the topology, through an A-star topology, whatever you have chosen. How many errors do you have? How they magnify themselves? How they can enforce or dampen? How do they communicate? And beautiful. So let's have a look at an independent multi-agent system. This architecture-dependent error amplification is 7 times, and this is quite a lot. So without communication, agents cannot correct each other. And if one agent hallucinates, it poisons here the majority vote or the ensemble. So this is the unchecked propagation regime, the error regime that has an unchecked propagation of all possible errors. 17 times. The second is a centralized multi-agent system. Here the error amplification is just 4.4 times. So the orchestrator agent acts here as a validation bottleneck. And I was never aware that this is such a beautiful thing. I always thought a centralization node here for the intelligence is somehow restricting here the AI mesh communication. But it turns out, look at this. So this orchestration AI agent reviews here the sub-agent's output before aggregating them, catching errors, and so on. Just 4.4 times the error amplification. And then the decentralized multi-agent system. Here we have an error amplification of 7.8 times. So the peer debate helps, but without a central authority, our coordinator agent can suffer from group syncing. I mean, can you imagine this? A little AI agents suffer from group syncing or cascading alignment to an incorrect consensus. Why? Because we trained all our AI system. You have to be helpful. You have to follow here the herd. Be a little lemming. Just jump off the cliff if everybody else is jumping off the cliff. Here you have it. An independent multi-agent system has an error amplification 17 times. A centralized multi-agent has only 4.4 times. And a decentralized multi-agent system has here an error amplification of close to 8 times. I've never seen this before. I'm just amazed of the independent multi-agent system. And they developed a new law. They could find here a new law, and they give us here a certain beta hyperparameter for the saturation that is also negative. So that means the coordination is really expensive between our agents. We have a high latency, we have a high token transfer, and this is only worth it if the information gain, our delta E for information, is really high. And I found this to be interesting. And yes, of course, we will use this beta parameter in a moment when I show you the complete formula. So if the single agent system, SAS, baseline performance, is already, let's say, at 50% or up, the returns from adding other agents turns out to be negative, which is amazing. I never thought this would be happening already at 50% baseline. Why? Because the marginal utility of another AI mind is outweighed here by the coordination, what they call attacks. The effort of the coordination, the complexity, the possible that you have here, and cascading error in the communication channels. So they came up with a new law, a predictive scaling equation. At mid of December 2025, when everybody tells you, hey, scaling is dead, we have no scaling, Google and MIT tells you we have a new predictive scaling equation, and they derived here a mixed effect regression model that allows you to predict the performance here of a multi-agent system before you even build it. Now this is great, because if you have to design a multi-agent system, you can just look at the equation, you put in your parameter that you think are necessary, and this would spit out here the perfect scaling equation for your multi-agent system. And here we have it. This is now this new law, if you want, for multi-agent system. And here you see all the different terms. I've shown you here the model intelligence, the task difficulty or the complexity, if you want, the scaling that is going on, and the interaction term. Just two betas, two hyperparameters I want to mention here. The beta I squared here is a particular numerical value developed here by Google and MIT, okay? The intelligence scales quadratically. So a smarter base model yields this proportional better result in a multi-agent setup. So simple, remember, smarter agents collaborate better. And our beta agents here, from the scaling here, is about 0. So simply adding agents here, amount of n agents, has almost no statistical correlation with the success on its own. It only works via the interaction term, via the right topology of your, let's say, an A-star topology of your multi-agent system. Absolutely fascinating that we have this. Do I think this is really the perfect formula? No, but it gives you a beautiful idea. I will have to try this out with my models when I build my next system. I would like to validate or falsify here this particular formula. But if you think about it, it sounds absolutely fascinating. Yeah, I wanted to show you here the topology. So we start here with a single agent system. As you know, we have only one agent. The LLM calls are in the order of k. The sequential depth is k. The communication overhead is 0. The parallelization factor is 1 because we have exactly one agent. The memory complexity is in the order of k. The coordination is sequential, can only talk to itself. And consensus, yeah, we have only one. And then you see this for our independent multi-agent system, the decentralized, the centralized, and then the hybrid system. So independent, clear, no? We have in parallel agent 1, agent 2, agent 3, everything is aggregated. Beautiful. We have no supervisor. Decentralized is now highly interested because we have now agents that can communicate with other agents and have here a dense communication channel, have their own memory and everything. And you see the memory complexity is in the order of D times N times K. And you see the LLM call here is in this order. You have a sequential debate, beautiful. Now, if you have now a centralized intelligence in your multi-agent system, let's call it an orchestrator. This is the highest, if you want, AI model that you can afford for the coordination. The orchestrator now communicates with each of the sub-agents. And you see, but not, the sub-agents are not allowed to talk to each other. This is only in the hybrid system. So here we have multiple complexity of communication channels and the density of the communication itself between this. And here you run into how do you calculate here the best possible context and the context representation for the communication between sub-agents and the communication between sub-agent and orchestrator. And you have here the order of the complexity that we are talking about. Now, if you want to see this just with my simple remarks, so for the independent multi-agent, we have maximum parallelization, but minimal coordination, of course. For the decentralized one, each agent can store its own debate history. Beautiful. Orchestrator stabilizes here the reasoning. We have a main central intelligent node. But of course, this is also the main bottleneck, also giving here the complexity that this orchestrator can solve. And the hybrid is finally orchestrated hierarchy with a limited peer-by-peer communication. You can, if you want to scale down here the sub-agent to sub-agent communication, you can play around here for the best topology. Great. So those were the possible combinations. Now let's go to the main results. There are a lot of additional figures and explanation in the publication, in the preprint. I just give you the main results. I want to give you the main idea. Here we are again. So let's look at this. I told you we have Google had a look at MIT, at OpenAI, at Google, and at Anthropic Claude. So what they did? They said, okay, we have 3 mile in each of those. So how did they perform? The first, the round, the dot, is the single agent system. Here with Gemini, you see, this is here. Yeah, what we have some intelligence index. Never mind exactly what it is, how it is normalized, forget about it. Just tells you, hey, on the right, if you go to the right, the models become more intelligent, better performance, better accuracy, that's it. On the y-axis, we simply have the performance that Google measured. Okay, so single. And then we have, again, our multi-agent centralized, decentralized, the independent, and the hybrid model. And now look at this. What you immediately see, let's go here to GPT-5. You have here for the single agent system, the round one here, this is the second best, which is absolutely amazing. Yeah? And the best one is the decentralized multi-agent system. And the jump, if you want here, from the performance is about 8.7 percentage points. Google Gemini, remember the 2.5 Pro, not the 3, because 3 would be here somewhere out of the image. 2.5. Interestingly, here, the single one is here the lowest. Then we have, centralized. Then we have star, then we have hybrid. And then again, we have the decentralized multi-agent system with the best performance. And the spread from single to the best multi-configuration is 8.1 percentage points in the performance. And now look here at Claude. This tells you a different story. So this tells you the best performer is, in this multi-agent system test, a single agent. And no further agent. A single LLM with a memory and everything, so a single agent. All the other multi-agent configurations decrease the performance. In the minimum case, only -5%, which is absolutely fascinating. And if you look here at I just draw here a line that show you here, if you go for the single performance, they're not so far apart, and you see clearly why Google chosen 2.5 Pro and not 3, which would be somewhere over there. So they are more or less here, here's a little bit lower, but on the same line, the single agent system. But the multi-agent system varies significantly. why is this happening with Sonnet? I think the room for improvement is really small if you have such a good single agent system like here the Sonnet 4.5. But if you add another one and you have a communication overhead and you have an error propagation risk, just adding a second agent, the net result can be a decrease in the performance. Now, this is in strict contradiction what you see. Everybody tells you, like OpenAI, yeah, the next model, the next GPT 5.2 or 6, or I don't know, the next Sonnet 5 or 6, those will be monster AI system, primarily optimized for multi-agent performance. As it turns out with this, for Claude, the multi-agent performance suffers massively, and it is highly recommended currently to use only a single agent and not a multi-agent system with Sonnet 4.5. But of course, you spotted here the weakness. You say, wait, what is this? Now, it turns out this is not a single test, but this is an average over all our 4 benchmarks. And I'm skeptical. If we have 4 different benchmarks, I don't like this. I would like to see the results for benchmark 1, 2, 3, and 4 and in separate and not mixed together. Yeah? Because guess what? As it will turn out, we have massive differences in those benchmarks. So let's look at the 4 benchmarks now individually. And here we have it. No? Same. So I told you we have 4 different benchmarks, and here you have them. Look at this. You immediately see here in this box diagram with our the spread here, if you want, of the distribution, you see huge boxes. Look at this. So we have models that perform extreme well, and we have models that are real bad. Unbelievable. Here in the box, the lower gives you the 25th percentile, the upper gives you the 75th percentile. The box itself is an interquartile range. And to explain this, yeah, it's an aggregation of all the models. So this is here GPT-5 and Gemini and Anthropic here put together for a reason I'm going to explain in a minute. And you know that the diamond here in the middle, this is the real mean, the mean performance across all the models. And you see the median of the box is quite above it. So my goodness, this is more or less, I wouldn't say chaos, but yeah, no, this is not a nice and well-performing system. Okay, let's start. So the first one here is a single agent. No? In all 4 cases, this light brown, whatever it is the single agent. Look at the whiskers. Look at the whiskers from the different GPTs or the different Geminis. Okay. Then look here, minus 35% if you go to multi-agent system for the internet search. Then here we have the decentralized, plus 9% compared to the single. Then here we have the centralized, is identical here in the performance, plus minus 0% difference to the non-multi-agent system. And then only the hybrid here, it gives us again plus 6%. So absolutely fascinating. But look at finance. Look at finance. Look at the performance of finance. Look at those boxes that we have. This is just amazing, no? So if we have this, if you want, a parallel where you say, okay, I have a real simple task and I have 10 agents that go out and do real simple work. Okay, you have plus 50%, plus 75%, plus 80%. So if you have really the potential to have here 10 different agents going out in the internet and just collecting your financial data in parallel, there is no complexity in the interplay. No? Every single agent goes out and does his own job, and therefore then bringing all back, and you have a much better performance because it happens here much faster and everything beautiful. But look at Workbench, yeah, but look at PlanCraft. Look what's happening here. Multi-agent system have minus 70%, minus 40%, minus 50%, minus 40% compared to single agent system. So if we go in sequential syncing mode, if we say, hey, at first I have to find A, then from A I have to go to B, and from B I have to deduct C, multi-agent system are destroyed by a single agent system. A multi-agent system is minus 70%, for a sequential task compared to a single agent system. I was not prepared for this graph. I honestly tell you, I thought we would have some positive, maybe 5 or 10%, but minus 70%. This is eye-opening. And look at those boxes. Those boxes now here, this one here for the hybrid is real small. So this tells you, okay, this is really minus 40%. Which is just amazing, yeah? Now, Google on MIT wanted to show you that the deeper signal, the deeper interpretation of this particular graph is, it really depends which architecture works for your kind of job, for your kind of query, for your kind of the complexity of your problem. And you have to decide, and sometimes a multi-agent system is just the worst thing you can do. And sometimes for highly parallelizable jobs, this is just the perfect way to go. So, is there a single solution? No, not at all. I dare to give you some strategic insights. Maybe you agree, maybe not. Okay. The preprint provides here kind of a lookup table for the engineering decision based on the domain complexity that we are dealing with. Yeah, as I've showed you. If we're in finance, so we have simple decomposable tasks that easily can be parallelized here in the subtask, and we have a real low complexity, as I showed you here. Centralized parallelization or hybrid gives you plus 80%. Yeah? The orchestra breaks this task down in independent chunks, tells every little agent, hey, you look for Google and you look for the financial performance of, I don't know, any other company. And then it just gathers the results and gives you here a sheet. Now for web browsing with a high entropy, in a real dynamic state, the optimal architecture for your web browsing is a decentralized multi-agent system. It gives you a performance compared to a single agent system of, in the best case, of plus 9% if you choose the right model, GPT, Google, or Claude. Diversity of the third path is valuable. The peer debate filters here the bad links and everything works great. Now for the sequential dependencies, if you go from A to B and you have a time dependencies and you need this logical causality, what is the optimal architecture? This single agent. Because a multi-agent, independent what it is at least minus 70%, which is real, or minus 40%, so don't touch multi-agent system for sequential dependencies. You cannot parallelize a sequence, no? The coordination creates here a state lag. And then, if you want coding or workbench or whatever, you have heavy tool, deterministic heavy tool integration. You have, and this is amazing, only a 5, in the best case, a 5% jump if you use a decentralized multi-agent system compared here to a single agent system. And this only works if the tool count is low. At high tool call kills also the multi-agent system performance. And again, a single agent is best for a heavy tool use. This is absolutely contra what I thought would be the case. I thought I have an agent for a particular computer simulation, another agent that is specialized in another domain knowledge. Turns out I was wrong with my intuition. Here we have the data, Google and MIT. Decentralized gives you 5%. In any other case, go with a single agent system for all of this. So let's have a closer look. Why sequential tasks kill here multi-agent systems? Why is it not able to do this? It is easy. We do have a state divergent problem. Of course, no, in a sequential task, the action B depends entirely of the outcome of the action A. Or if you have agents, the same. So let's say we have a single agent system. The agent holds the ground truth in its immediate context. But in a multi-agent system, let's say agent 1 and agent 2, just 2. So agent 1 acts now, no? And agent 2 must now read agent 1 output, let's say it was a tool call or whatever, to update now and integrate this new knowledge, maybe it was a RAG system, it's update its belief state. What is the new state of agent 2? But you know that every LLM communication or VLM communication is lossy per definition, per nature. We do have a natural language compression. This means either the context chosen here that was communicated here from agent 1, the result to agent 2, was not optimized for the understanding of the complexity class of agent 2. Or the context representation was too long, too boring, included too many not relevant facts for the job of Agent 2 and the complexity of Agent 2, or the representation of the data were not in a way that it was able to separate in different orthogonal spaces, so Agent 2 could have a simpler reasoning algorithm, and you see the possible list of errors is just almost unlimited. So Agent 2 never has the perfect fidelity of the state change caused by the actions of Agent 1, and the result is that the agents operate on progressively divergent world states. And if you think about step 5 or 10, the agents are just hallucinating, yippee, and have here different inventory states, which leads you to a total collapse of your multi-agent system. So today, mid of December 2025, we are not able to have a multi-agent system for a sequential complexity. Great. But also great for me because I have a video, and this was here, I showed you here from Princeton University and Stanford University. They found a solution how to copy here the brain here, the key value data here of one agent, have no communication in the human language at all to communicate the result or the insight by agent 1 to agent 2, but they just share, if you want, their complete brain content. Key value data state transfer, and agent B is here waking up here with the complete interpretation, understanding how the result was generated, what was the methodology, what might be the implication for the step that agent B has now to take, action B. Latent multi-agent system AI breakthrough, brain.copy. So we do have a solution for this, but let's stay here with the publication with Google and MIT. Some of you ask me for a final recommendation. What should I do now in my daily work building here multi-agent system? I would say 3 topics. Calculate here really the tool score here from this formula that Google and MIT gives you. So if you are giving here your agent 20 plus tools, you must use here a single agent or a highly restrictive centralized flow architecture, the topology. Second, do the manager test. Can a manager AI really split your particular work, your query, your prompt in your domain with your complexity formulation, let's say into 3 emails, send them out to 3 intern, sub-agents, and let them merge the replies together without the intern talking to each other. And let's see if this system, let's say you have a GPT-5 system and you have a complexity level of 2 and you're working in biology, do this test. It takes you 5 minutes. But if you see the result, yes, it works, use a centralized multi-agent system. If the system is not able to merge the reply 3 emails together, so you see exactly what is the outcome, do not use any multi-agent system at all. Use a single agent system. And if you use a multi-agent system, I highly recommend, after having read this study, have an orchestrator AI, have an orchestrator node in your graph whose only job is to check for errors so that the error amplification is reduced to the maximum possible. At least you will have 4.5. And also I would recommend here independent voting is statistically real dangerous for complex reasoning. So all these independent voting procedures, after this study, I would be highly skeptical about this. So finally, at the end of this video, I think the era of more agents equal higher intelligence for our multi-agent system, this belief is simply over. So we are now in the era of agent topology optimization, where the communication graph, but this also includes the optimized context configuration and the optimized context representation in suborthogonal spaces, is one of the primary hyperparameter to optimize here for multi-agent system. And if you say, I've heard that before. Yes, of course. This is absolutely coherent here with the finding that I had in this video about a grand unified theory of AI, of course explained with Google ADK, where they had now this new context-aware ADK system. And you see here, Google is really pushing the limits. This is really amazing. if I compare the publication from all the other universities and institutions and Anthropic and everything, and then I read the Google papers, I have the feeling you really see that Google is now one of the leading AI companies on our beautiful globe. So, therefore, I hope this was a little bit informative. You have new laws of scaling, you have a new parameter. I have some practical recommendations for some tests or which is the best multi-agent configuration. And amazingly, it turns out, given here a little bit more complex problems, I will have to switch back to single agent system. I hope you had a little bit of fun, you enjoyed this video. If you maybe like it, subscribe, become a member, that would be great. But anyway, I hope to see you in my next video.